I'm Steve Chilgrad. I'm the research translation leader for the Columbia Superfund project, and I also collaborate on some of the science projects. But it's my pleasure today to introduce the second talk by Dr. Basu Anirban. Basu did his undergraduate at, let's see if I can pronounce this, Jadavpur University in India. He got his PhD from Illinois at Urbana-Champaign, and then was a postdoc at UC Berkeley in the Berkeley lab. He's currently a lecturer at the Royal Holloway, the University of London, and he will tell you the topic of his talk today.
Wonderful. So let's see, we have the transition of slides.
Yeah, so I'm going to share. Okay. All right. Thank you very much for the introduction, and thank you very much for inviting me to give this talk. Catherine already has set the stage for isotopic fractionation by introducing a lot of ideas. In this talk, what I'll do is start with uranium geochemistry, and then discuss uranium isotope fractionation and what we know about uranium isotopes from lab experiments, and then use one example of application of that in a larger scale field site where we can sample groundwater. So the photo on this slide is a photo of the uranium mine at Smith Ranch, Wyoming. So if you look closely, you'll see this PVC pipes sticking behind this tanker, this PVC pipe. These are really the mines, because that's how they inject oxidants in the mine and then get the oxidized uranium, which is soluble, out. So uranium is quite an important element for energy resources, and particularly used in weapons manufacturing and military industry, led to piling of global mine tailings and contamination of soils and sediments and groundwater. So if you look at the US, 36 states, there are contamination reported from 36 states, and globally about more than 1 million cubic meters of mine tailings already accumulated. Now this is the data, I'm quoting an old data, so now it's probably several million cubic meters of global mine tailing. And isotopes are particularly useful and being used to track contamination, and a new field is emerging now, use of uranium isotopes and uranium concentrations to understand the health of past oceans, particularly to track ocean anoxia and calculate the extent of it. So I'm not going to go into details of this, but uranium isotope systems are particularly very useful in tracking that. So if uranium mine tailings are exposed to oxygen in the air and rainwater with dissolved oxygen, they're very easily oxidized to uranium-6, which is soluble. Now, if you reduce uranium-6 to uranium-4, that lowers the solubility of uranium by 4 orders of magnitude. And this is a really good strategy for remediating uranium contamination. A diverse group of microbial community can reduce uranium-6 to uranium-4. I have a couple of examples here, 3 examples. Anaerobictobacter is a soil denitrifying bacteria, and then two metal reducers, Geobacter and Shionella. They're very efficient in reducing uranium-6 to uranium-4, and they oxidize organic carbon, and then couple that oxidation with reduction of uranium. And particularly this reduction reaction is quite energetic for bacteria, and it produces more energy than sulfate reduction and some iron reduction. So that's the incentive for the bacteria, why bacteria would do it. Now, the obvious question is, how can we track this uranium reduction, which is a strategy for remediation? Can we track it by just looking at uranium-6 concentrations in the aqueous phase, in dissolved U6 in groundwater? Concentrations are particularly affected by a series of physical and chemical reactions, for example, dilution, dispersion of the uranium plume, and absorption of uranium on mineral surfaces. But uranium isotope ratios are much better proxies to track these redox reactions, because isotope ratios are affected only by reduction of uranium-6 to uranium-4. So Catherine already introduced basics of kinetic isotopic fractionation, and I'm not going to go into details of that. Here I have an example. So if you're looking at biodegradation of something with light isotopes, carbon-12, and heavy isotopes, carbon-13, and this is an example here, light isotopes react at a faster rate during this reaction. So if you, after a while, if you look at the remaining reactant, you'll see that the reactant is enriched in the heavier isotopes. So that's the regular kinetic isotope fractionation, where the remaining reactants are enriched in heavier isotopes. That works for chromium, that works for selenium, and pretty much the rest of the periodic table, except for uranium. They behave differently. Now, uranium has 3 isotopes, and we can call them stable at environmental timescale, decadal timescale, because their half-lives range from several 100,000 to several 100 millions to actually 4 billion years. And the most abundant isotope is uranium-238, and then uranium-235, and very tiny amount of uranium-234. And reduction of uranium-6 to uranium-4 induces isotopic fractionation. So they separate 238 from 235. And in this case, unlike the lighter elements, uranium-238 is more reactive. And the theory is given by this idea of nuclear volume effect. That's an equilibrium isotopic fractionation, where nuclear shape and size determine the isotopic fractionation. Now, if you look at uranium-238 and uranium-235, and the electrons, particularly closest to the nucleus in the s orbital, and how much attraction they feel for these 2 isotopes, that's given by this Coulomb potential. And x-axis is distance from nucleus. So if you look at the large nucleus, that's 238, it has a shallower potential compared to the. So what it means, the less strongly bound to the nucleus. They feel less attraction. And that also means that uranium-238 has lower electron density at the nucleus. Now, if you look at the geochemistry of uranium species, uranium-6 has the electronic configuration of radon, while uranium-4 has 2 5f electrons. Because of the presence of these 5f electrons, these electrons screen s electrons. So that means these 5f electrons lower the electron density at the nucleus. So what this translates to is uranium-4 has the right space to accommodate 238, and that lowers the overall energy of the system. That's why 238 is favored in uranium-4 species during a reduction reaction. So this is a nuclear volume driven equilibrium isotopic fractionation. And if you look at the reactions in a well-mixed batch reactor, what you'll see is something like this, that in this plot, I have delta 238 uranium, and definition of delta is given by this equation here, which is 238 to 235 ratio relative to a standard expressed in terms of per mil. This ratio in the remaining reactant, that's uranium-6, follows this blue line. X-axis is the fraction of reaction. So after 20% reduction, delta 238 values are already lower than the starting point. And then as the reaction proceeds, it becomes lower and lower, so it becomes more negative. What this means is the remaining reactant is being enriched in light isotopes, so 235. So 238 goes down, delta 238 goes down, that means enrichment in light isotopes. If you look at the reaction product, that's being enriched in heavy isotopes. And the difference between this is the size of fractionation. So that's the fractionation factor, which is given by this alpha. And according to this equation, so that's basically 238 to 235 ratio in reaction product over the same ratio in the reactant, that's uranium-6. And we express alpha in terms of epsilon, which is another per mil quantity, just to look this alpha, make it look bigger and a whole number. So the utility of this is if you have a semi-closed or closed system, and aquifers, sometimes you can model them as semi-closed systems, then the utility of this is if you get a water sample, you can measure delta 238 uranium value in that water sample very easily. So the fractionation factor connects the isotope ratios with how much uranium is reduced by this fractionation factor. So we can, from the water sample, we can get the value of how much uranium is reduced when the sample was collected in that sample. I mean, it's not particularly a good approximation, but this Rayleigh type distillation works for aquifers to some extent. Of course, we need more complicated reactive transport models, but this is a good way to show why uranium isotope ratios provide us with more information than we cannot get with the concentrations alone. So this, in this sense, it's a really powerful tool to understand what's going on with uranium in terms of oxidation and reduction in the system. So what's really important in the system is to understand what this curve looks like, and that's determined by the fractionation factor. So we need to understand fractionation factors, how much they are, and what are the controlling factors. So with that background, now I'm going to talk about the microbial experiments and the fractionation and try to make sense of fractionation factors. And then I'll talk about abiotic and then move on to the field studies. So the starting point was this paper that came out in 2006. This is the first paper that tried to determine the fractionation factor for microbial uranium reduction. Now, this is really interesting that this is the starting point of the experiment. If you go this way, that's the direction of progressive reduction. And delta 238 values are increasing this way from bottom to the top. Now, this is a starting point, and with progressive reaction, what's happening is the remaining reactant, and they're looking at the remaining reactant, is being enriched in heavier isotopes. So that's exactly the opposite of what the nuclear volume fractionation would predict. A few years later, this is the first biostimulation experiment at the rifle site where they injected acetate and did biostimulation and measured the isotope ratios in groundwater samples immediately after acetate injection. What they found was as the uranium concentration went down, delta 238 values decreased and went to more negative values. So this is what nuclear volume effect actually predicts in the remaining reactant enrichment of the lighter isotopes, 235 uranium, because the heavier isotopes are going to the reaction product. So early lab experiments contradicted the field observations, and that's when I started my experiments to understand the fractionation, what really happens during microbial uranium reduction, and if these fractionation factors vary based on the metabolism, and if there is a kind of a single value that we can use for environments that are nutrient poor, like natural environments. So I did the experiments using 2 different metal reducers. So I used 2 different strains of geobacter, 2 different strains of this soil denitrifier anaeromyxobacter, a novel strain of Shivonella, that's another metal reducer. And all of these are gram-negative bacteria. That means they have a cell membrane with 2 membranes, inner membrane and outer membrane, and space between them. And then I also did some experiments with this gram-positive bacteria. So they have a very different cell wall structure, what the enzymes are. This is desulfidobacterium Viet1. And the goal was to see what really happens during the experiments. So these are batch incubation experiments at relatively low cell density compared to other experiments. So during these experiments, with time, the uranium concentration went down systematically. This is an example from geobacter sulfur reducents, and nothing happened in the cell-free controls. So that means bacteria are actively reducing uranium-6. And when we measured the isotope ratios, the delta values went down systematically following a Rayleigh type distillation that can be modeled using a fractionation factor of 0.7 per mil. So that's all good because it confirms the theoretical prediction. It's in the right direction. It's all good. However, when I put all these values together, what I see is there is a range. So the maximum fractionation predicted by the theory is about 1.3 per mil. And this range I found in the experiments is from 0.7 to 1 per mil. So that's really a large range for uranium. And this type of range was confirmed by subsequent studies, by Stilo, by Claudine Starling's work. So this is quite a large range. And the first question is there any systematic variation between this 0.7 to 1 per mil? So to understand that, when I plotted the fractionation factors against the reaction rate normalized by the number of cells in the experiment, what I saw was there is an apparent pattern. In this case, I'm seeing, so x-axis has the rate and y-axis has the fractionation factor. And all of these experiments are pooled in one plot. What I'm seeing is at low rate, I have large fractionation, and high rate, I have a smaller fractionation. But it's not really very convincing because I don't really have many data points between these two. But this gives kind of a direction from this point that, okay, so what I can do is see how these bacteria actually metabolize uranium and design some experiment to test an idea coming from the mechanism. So one of the most well-studied strains is Shivonella, and what we know is the enzymes responsible for uranium reduction are either in the periplasmic space between 2 membranes or on the outer membrane. And when you see the reaction products, so these are uranium-4 nanoparticles between cell membranes, and sometimes they're associated with outer membrane enzymes or even with extracellular polymeric substances secreted by the cells. Now, we are sampling from here, and this is the bulk solution where uranium-6 is dissolved. the reaction is happening on the cell surface or inside the cell membrane. So there is a separation between the bulk solution and where the reaction is happening. Now, this is observed in other systems, and the question was, okay, so how does this affect isotopic fractionation? To test this idea, I designed a whole bunch of experiments where I varied uranium-6 concentrations and used only one strain, Shionella, because that gets rid of any species effect with all other species in previous experiments. And we used some reactive transport simulations to test our conceptual model, which assumed that separation between bulk solution where uranium is dissolved and where we are sampling from, and where the reduction reaction is happening. So we did find a large variation for this one strain. And it seems like that the fractionation factor that's on y-axis and initial uranium concentration in the experiments on x-axis, the fractionation is dependent on the initial uranium concentration. Now, this is not really very intuitive. So we wanted to make sure that what we are seeing is really reduction, and we did some Zane's work on the reaction products at Argonne National Lab, and that told us that, well, the uranium products are more than 90% uranium-4. So that's good news. We're seeing reaction. Now, when we looked at the first-order reaction rate constants normalized by number of cells and the initial concentration, we do see a correlation between rate constants, normalized rate constants, and the initial uranium concentration. And it becomes even more obvious when we see the fractionation factors against the normalized rate constant. So it's really clear dependence on the rate. And we are seeing large fractionation at lower rate constants and smaller fractionation at large reaction rate constants. Now, this idea is actually well developed in chemical engineering for solid catalysts. So if you have a solid catalyst and the reactant, liquid reactant, dissolved reactant, has to work, come and diffuse to be able to react on the surfaces, usually the way it's conceptualized is we have the catalyst, and around the catalyst there is this zone where the concentration is low, and this is a boundary layer. So the reactant must diffuse through the boundary layer and come to the surface where the reaction is happening. And it looks somewhat like this. This is the catalyst surface, and this is the bulk fluid separated by this boundary layer. And you can calculate the flux of fluid coming in using a very simple fixed law type equation. So we applied this idea to the experiments that I have done. Now, based on this, we developed a conceptual model, and this numerical simulations are done by Christoph Warner at University of Bern, and we used Tough React and the model that's developed primarily by Eric Sonnenthal at Berkeley Lab. What we are doing here, that we are seeing this cell. We are not looking at the inside of the cell, and we're assuming that there is a boundary layer around the cell. So this white region is the boundary layer. This blue region is the bulk fluid where uranium is dissolved. Uranium has to come inside through this boundary layer to be able to react with the enzymes. So that's the conceptual model. And we can calculate the diffusive flux of uranium-6 by this equation. Now, all these parameters are unknown at this point. Some of them we got from the literature. But for the others, we had to calibrate the model. Before that, let's look at the reaction network for simulations. So we used oxidation of lactate and oxidation to acetate, basically. And we used two different isotopes with the same reaction for our reaction network. So we are considering these two reactions for uranium reduction. Uranyl is becoming uranium oxide solids. We are treating these systems using a transient state theory type rate law, where the rate is rate constant times 1 minus Q over K, where Q is the ion activity product and K is the equilibrium constant. And fractionation factor really is the ratio between two equilibrium constants for these two isotopologues. We are assuming the fractionation factor is an equilibrium nuclear volume dependent fractionation factor of 1 per mil. So we are putting in a fixed fractionation factor. And we use tough react to simulate reduction and isotopic fractionation. So what we see is first the calibration of the model. So we calibrated the model with 18 micromolar uranium-6, initial uranium-6 experiment. So this is the experiment with the highest uranium-6, initial uranium-6. Adjusted the parameters until the simulations matched the data reasonably well. So this is for the concentration, the right-hand side for the isotopes, delta versus natural log of fraction of uranium-6 remaining. So natural log linearizes the plots. So the simulations match the data at this point really well. So we fix the unknown parameters at this point and use those for the other initial uranium concentration experiments. So if you look at the simulation results, all of them produce a nice Rayleigh type fractionation, which is exactly what we observed. The values of fractionation factors are very close to what we have observed. So simulations are reproducing the observations really, really well. Now, if you look at the results of our model, these are the blue dots, and the experiments, these are the reds, really nice match. And we do see the rate dependence on fractionation. So what these simulations are telling us is the reaction is really a two-step process. First, we have diffusion of uranium-6 through the boundary layer around the cell, and then reduction on the cell or inside the cell at the enzyme. Now, the variation of fractionation is really dependent on the reduction rate. How it works? At a rapid reduction rate, both of the isotopologues, so uranium-238 and 235, in its hexavalent form, is being consumed very quickly. So there is no concentration gradient that can develop across the boundary layer between the pool, outside bulk pool, and the enzyme zone. But if the reaction is really slow, then uranium-238 is preferentially consumed, and that leads to the development of two different concentration gradients. Concentration gradient of uranium-238 is then enhanced because it's consumed more. So uranium-238 is diffused more through the boundary layer. In the bulk pool, we are depleting 238, enrichment of 235. So this is really what's happening behind the scenes. And a variation of this model, it's really versatile. A variation of this model we're using to explain the selenium data that Catherine presented from the cross-hole test. So this is a summary of microbial experiments. Let's take a very quick look at the abiotic uranium isotopic fractionation at this point. And it started with a bit of a controversy that this paper that came out in 2015 claimed that there is no fractionation during abiotic uranium-6 reduction. So they used several iron-2 reductants that are known to reduce uranium-6 to uranium-4. And when they conducted these batch experiments, they found no change in delta values with a fraction of reduction. So x-axis is concentration over initial concentration, so no reduction, 100% reduction. And there is no change, particularly for hydrogen sulfide or iron sulfide. Now, they did the reactions in a particular way. The experiments had almost no complexing agents like bicarbonate or calcium. So uranium was removed by quantitative absorption on the minerals within first few minutes of the experiments. And then there was a subsequent reduction on the mineral surfaces. But that's not quite what we see in the environment, because wherever you sample groundwater or pore water, even river water, lake water, we usually have quite a bit of calcium dissolved in water. And it's well known that uranium adsorption is highly influenced, particularly above pH 7, by the presence of calcium. So this is a paper where they experimentally determined the fraction of uranium adsorbed with pH. And you do see that between 2 to 10 millimolar of calcium, the adsorption is really low above pH 7, adsorption of uranium. And if you have a lot of calcium, the dominant uranium complex is calcium uranyl carbonato species, which is basically chargeless. And this is a very common species that we find, for example, rifle groundwater is composed of 97% of this neutrally charged uranium. So 97% of all uranium is neutrally charged in rifle groundwater. So we used this idea and we systematically varied fractionation varied adsorption systematically by adding calcium to our system. So we had 4 sets of experiments. First one, on the left panel here, so y-axis is showing the delta values, x-axis is the fraction of reaction. This is the beginning of the experiment, end of the experiment, 100% reduction here. When there is no calcium, we see a small fractionation. With progressively increasing calcium, the fractionation actually increases. And when we plotted the fractionation factors against the neutrally charged uranium, almost a 1-to-1 correlation between fractionation factor and the neutrally charged uranium. So the take-home message is abiotic uranium reduction does induce significant fractionation in the same order as the microbial fractionation, in the same direction. But if you take a closer look, if you take a deeper look, here is the rate dependence of abiotic reaction. So what calcium is doing, really, it's slowing down sorption. That means it's slowing down the electron transfer from the surface to uranium. So we do see the same rate dependence, although I haven't yet modeled this system, but we do see the same rate dependence, a very strong correlation between the fractionation factor and the first order rate constants from the abiotic reactions. So now with this background, if we look at how we can use this idea to trace uranium redox and mobility in groundwater systems. So the best way to understand this is to look at places where we expect a lot of uranium. And uranium roll fronts are one of those places where redox naturally creates this uranium ore deposits. This cartoon shows how it works. So if you have an aquifer where there is a redox front, where oxidizing conditions becoming reducing conditions progressively, if you have a granitic source where uranium is being leached from and being transported by the groundwater, once dissolved uranium-6 hits this redox front, it's reduced, and uranium-4 is precipitated. Usually the reductants are either hydrogen sulfide gas or iron sulfide or microbial biofilms, but that's how uranium deposits are formed over millions of years. And as Catherine already showed you, that we have here a very systematic order of reduction based on the redox potential. So first we see selenium reduction, and then uranium, and then molybdenum, and then sulfate. Any uranium deposit shows the same pattern when you look at the solids. So first thing you see is selenium enrichment, and then uranium enrichment, and then molybdenum enrichment, and then you have some sulfides here. So this is the anatomy of any uranium deposit. They may not be highly enriched and economically viable roll fronts, but if you have in the flow path of groundwater any uranium reduction, it should follow the same pattern, same trend. So our study site is in South Texas. It's where this pin is. The name of the mine is Rosita Uranium Mine. For your reference, here is San Antonio. Houston is on the top right corner. And it's not just one tiny deposit. There is actually a very systematic pattern where all these tiny blue dots that you can see here, these are the roll front deposits, they're concentrated, and they apparently form within this ancient fluvial megachannels. So, and if you look at the map view of a roll front, they do look like a paleo channel, basically. So the way it works is, again, you have to have some granitic source. The groundwater brings in these uranium, you have the redox barrier, and then that forms all these uranium deposits. They're very well mapped, not only in Texas, South Texas, in Wyoming, in South Dakota, Colorado. They're very well mapped. In South Texas, though, they were produced when these deltas formed, and normal faulting provided the conduit for this hydrogen sulfide gas from hydrocarbon deposits in the down gradient part to flow and to reduce uranium. So that's the geologic setting for the formation of this deposit. The way these are mined by oxidation of the uranium ore body, where solid is oxidized to uranium-6, which is soluble. Now, the worry of these mines, and this is probably a systematic problem wherever you have uranium deposits and they're being slightly oxidized and releasing uranium in soluble form, what happens to that uranium that's being released as soluble form? For this type of site, the hypothesis is that when they're released, they interact with these reduced minerals here or biofilm, either iron minerals or bacteria, and they're reduced exactly the way these deposits were formed. Now, if that's the case, we should be able to see the evidence from the isotope ratios, because the uranium concentration is going to be really low here and here. And if this is reduced, partially reduced, the uranium concentration is also going to be low. So just looking at the uranium concentration is not a very reliable indicator at all for this type of setup. But it will be very pronounced if there is any reduction going on in this part from the uranium isotope fractionation in groundwater. So what we have done is, this is the map view, and this gray shaded area is the roll front. We collected water samples along the transects parallel to groundwater flow. Each transect has an upgradient monitoring well, a well drilled within the ore zone or in the roll front, and then a downgradient monitoring well. So groundwater flow is this way. And we characterized pretty much every isotope system from nitrogen to sulfur. So here, I'll just very quickly show you two different isotope systems, three actually, two different uranium isotope systems and sulfur isotope systems. So first, the geochemistry of the groundwater. These four panels show, top left one is the EH. So it shows a range from quite negative EH to plus 100 millivolts. Particularly, the ore zone is very reduced in parts. And in general, the downgradient wells are quite reduced. And the nitrate is concentrated mostly in the upgradient water, in the ore zone and downgradient, very low nitrate. But then in the downgradient and ore zone, you see increase in dissolved iron and dissolved manganese concentration. So this tells us that this part of the site is under iron and manganese reducing environment. And then if you look at the uranium isotope ratios, which are plotted as delta 238 uranium values against uranium concentrations, all these circles are from groundwater samples collected from within the roll front. So these are the ore zones, and they plot 0 or above. That makes sense because uranium-238 preferentially goes to the uranium product phase, so they're isotopically slightly heavy. But if you look at the downgradient water samples, they're highly fractionated. And we are seeing a fractionation of about 3 per mil, and that's as much as you can see in any system, really. So we do see a slope, a trend here. And if you plot the natural log of concentration versus isotopes, the slope gives us the fractionation factor. And we see a fractionation factor that's about 0.5 per mil, which is almost the same as the early reports from the rifle site for biostimulation. So fractionated delta 238 values can only be generated by uranium reduction in the downgradient part. It becomes a bit more apparent if you look at this transect. So this is an unmined part. So this ore zone is not disturbed by addition of oxidants. We have 2 transects here. If you look at the uranium isotope ratios, the eastern transect is highly fractionated as you go from upgradient to downgradient. So this part is really uranium reducing, particularly the ore zone and the downgradient. However, the western transect isn't really that fractionated. Rather, it shows the values similar to that of the ore. So that means it's not quite reducing enough to reduce uranium. However, how far is it from uranium reduction? Now, this is where selenium isotopes come very handy. So if you look at selenium isotopes, it does show a huge fractionation from 2 per mil to 6 per mil. And by the time you collect samples from the groundwater samples from the downgradient, there is no selenium detectable in the sample. So selenium is gone. So this means that this is not really oxidized, but it's very close to selenium reduction, which is right above in terms of EH, uranium reduction. So this is the last tracer, pretty much. And this is a radiogenic isotope system. And we are looking at uranium-234 over uranium-238 activity ratio. So in any reasonably old sample, this ratio should be in secular equilibrium, which is 1. Now, if you have a grain where uranium is sitting right at the boundary, grain boundary, then as it decays by an alpha decay to thorium-234, and then eventually to uranium-234, alpha decay has a recoil effect. The parent nuclide, then the daughter nuclide, then actually pushed by about 30 nanometers, 30 to 40 nanometers. So if it's sitting at the grain boundary, it can be ejected outside the grain and end up in the surrounding water. That's how the water can have higher activity ratios than secular equilibrium value of 1. And this grain will then have much lower activity ratios than 1. We have collected samples, and I'm showing 3 transects here, one from unmined area, PA4, so this transect, and these are 2 mined areas. If you look at the ore zone groundwater, the values are very similar. It's about 0.75, the activity ratios, which is really low. And from ore zone, if you go toward the upgradient or downgradient, the activity ratios increase. And they reach a secular equilibrium value, sometimes even more than the secular equilibrium value. So 2 things. One is, then this ore zone water has this unique signature. So that's a tracer for ore zone water. If this water is flowing to downgradient wells, the downgradient water should have the same value or slightly higher value that should be predicted, that we should be able to predict based on the alpha decay in the system. what we are seeing is much higher than that. That means that this water is not making it to the down gradient well. So this pattern suggests that there is a loss of uranium in the ore zone or between the ore zone and the down gradient well, which is a good news for this site. Now, an additional tracer we found out, which is also a very good tracer for the ore zone groundwater, is sulfur isotope ratios in water. So if you look at the sulfur isotopes in sulfides in uranium ore, they have really low values because they are usually biogenic. So that means light sulfur isotopes are reacting preferentially when they're forming sulfides. Sulfides have very low delta 34S values. And when they're oxidized, they inherit the signature of the ore. So all the ore zone wells, they plot together. And this is from an unmined area. So for all the mined area, high uranium, they plot together. If you look at all other samples, there is about 20 per mil variation between these two. So we found out that, okay, so we can look at sulfur isotope signature of the ore zone groundwater. That should tell us if it's just moving without any reduction reaction in terms of sulfur, or if it's changing. So if its value is going down, that means further sulfur reduction is happening. Oh, sorry, value is going up, further sulfur reduction is happening. Okay, so this is my last slide. The conclusions is basically we can use the uranium isotope ratios very effectively to delineate the zones of uranium reduction. And then we can use a couple of additional tracers, uranium activity ratios and sulfur isotopes. And this is applicable to any groundwater system with a well-developed redox system. It doesn't have to be an economically viable ore deposit. If there is a little bit of uranium reduction, that should be picked up by the isotope ratios. So the acknowledgement slide. So these are the people who were extremely helpful and instrumental for getting all this data. And with that, this is my last slide. Happy to answer any questions you may have.
Good. So we cannot see any questions that people have typed, but I hope people have questions for you, Anirban. And myself, I have some questions. I have some maybe more specific and some more general that maybe I'll keep my general question for later. So regarding what you are showing us, it seems that you could then modify how this uranium is being reduced and in order to try to control it in the environment. It seems, am I understanding this correctly? Like either with bacteria or through other mechanisms, you could try to influence how the uranium is being kind of moving around in the environment. Is that correct? Or this would be too much to think that it's possible?
No, it is entirely possible, and it is how it's done. So if you have bioremediation, we are using bacteria and we are just promoting the growth by adding nutrients to them. And in some cases, you can inject abiotic reductants. They reduce iron 3 mineral to iron 2, for example, sodium dithionite. You can even inject sulfide. Well, it's very toxic, but it's possible. So both abiotic and biologically, you can induce uranium reduction. And what I have shown is if it's happening naturally, isotope ratios are telling you where it's happening. And if, so you also see the reactive transport. So as the fluid is moving through a zone of reduction, you see the signatures evolving. That's one thing. The second thing is for active bioremediation sites where we have high rates of reduction, we can modify the fractionation factor to accurately predict how much uranium is being removed. And that's also possible for abiotic engineered sites. Hmm. In general, reduction is the only way to fractionate uranium isotopes. If you have adsorption, so you can have huge amount of adsorption taking all the uranium from solution onto the mineral surfaces, but that's, that reaction doesn't induce any isotope fractionation in the same direction. It does induce a tiny isotope fractionation in the opposite direction. So then in the groundwater, you'll see completely a different signature. And what our model does, it can actually differentiate between all these reactions. So for example, for selenium, when we are using a similar model, we are adding a sequence of reactions. So first is advection of selenate, and then rapid advection of selenate, and then slow reduction of selenate to selenite. Some of the selenite is being absorbed, and you can add the fractionation factor. So we are using a fractionation factor for reduction, which is 8 per mil, and then the model generates exactly what we are observing. So that's the strength of the model, that it mechanistically generates what we are seeing in the experiments. So in short answer is, yes, we can do both abiotic and biological treatments and use isotope ratios to characterize what's really happening.
And it was actually useful to hear you explain it again. And Steve has a question. Steve?
Yeah, just a follow-up to Anna's question. So if you're going to reduce the water to get rid of the uranium, since you're talking to a big arsenic group, what are you going to do to the arsenic at the same time?
That is a big worry, because if you have iron reduction, aqueous iron 2 reduces uranium at a quite a slow rate. But if you have surfaces, then absorbed iron 2 on surfaces, they reduce very efficiently. But that is a big problem, because if the remediation, so that's why I think uranium isotopes are very useful. You can actually, not only uranium isotopes, but entire, whatever isotopes you can measure, for example, from nitrogen isotopes and oxygen isotopes, giving you denitrification, to all the way to sulfur reduction. If you can pinpoint the existing redox environment, and we have done a little bit of that using both selenium and uranium isotopes, that it's not quite uranium reducing, but selenium reducing, that helps you to decide what kind of remediation treatment to use. If you go for very aggressive remediation, that will very likely release all the arsenic, because if it reduces all the iron surfaces, then you'll have a huge amount of arsenic release. That is a big problem. So that's why it's really important to understand what's happening in terms of redox already, and how much we need.
Mm-hmm. And Ben has another question. Ben?
Yeah, so another one about the fractionations. How easy is it to distinguish between enzymatic reduction and secondary reduction? So for example, bisulfide, because they both fractionate uranium. But how different are the resulting isotopic compositions, for example, of the solids or the aqueous uranium?
I don't think we can effectively distinguish between two different mechanisms.
Yeah.
But if one is happening at a faster rate, so I would expect because the uranium as a sole electron acceptor is not very energy producing for the bacteria compared to a lot of other electron acceptors. So the predicted growth is less so measured growth is less than what's predicted. So if you have a system where active sulfur reduction is going on, I would expect sulfide to reduce uranium at a much faster rate. So in that case, we should see a little bit of lowering of fractionation because of a high rate compared to biological fractionation. But I don't think we can distinguish based on the fractionation factor. And this is the same story for all metals. So for example, chromate, we pretty much have the same fractionation for say aqueous iron 2. When you reduce chromate by aqueous iron 2, the fractionation is 4.2. And for Shionella MR1 strain, the fractionation factor is again exactly 4.2. So it's really difficult to distinguish between abiotic versus biological. And that's what we tried to understand. That's why we kind of took the shortcut of avoid this biological complex mechanisms on the cell and just assume a diffusive boundary layer, what the catalyst people do, and see if we can reproduce the same. And it looks like it's pretty robust in that sense that it has to be, there has to be a boundary layer where the concentration is lower compared to the bulk fluid. That's the only way we can see the rate dependence, but not the dependence on the mechanisms.
And one more related question.
One thing just I would like to add, that we don't know fractionation factors for all abiotic reactants. And because uranium is so strange, it is possible, I don't know how likely, that some abiotic reactants, depending on how much energy they produce, will have either higher or lower fractionation factors, significantly different from the others. So we know very little for abiotic fractionation of uranium, because only mineral so far tested is iron sulfide. We did that experiment. Right now I'm working on uranium reduction by siderite. So, and we don't know about zero valent iron yet. That's on my list of experiments. So basically, no.
And related, has there been a measurement of the two steps of uranium reduction? So where the fractionation results, is it in the uranium 5 to 6, or in the 6 to 5, or the 5 to 4 step?
No, it's also another problematic part. So if you have a lot of uranium 6 to begin with, then disproportionation, in my opinion, is very likely, because then you can have a lot of uranium 5. And this can be tested with something that can donate only 1 electrons, and we can see how much uranium 5 we are producing and the fractionation. But it's a very tricky experiment to design. So first of all, that we don't know whether it is possible to have direct 2 electron transfers, 6 going to 4. Just a few months ago, I think in January, another paper came out from the Manchester group. They found uranium 5 as the main reaction intermediate for biological experiments. It could be that it's the only way. It could be also possible that there are 2 electron transfers at a time. For chromate reduction, we know that for aerobic reaction, that it is even possible to do 3 electron transfer at a time. For uranium, we don't really know that. So, and the fractionation is not measured for each step. As very, I can't think of experiment. It's going to be really difficult to measure that.
Good. So it's 5 p.m. So it's kind of the end. But before finishing, I wanted to ask you why arsenic doesn't have any isotopes. Maybe there is no answer to my question, or maybe my question is stupid. But
if it had, then it's probably I don't know the exact answer, but it's a nucleosynthesis. I believe that's the the stability range. Maybe but if it did have, then I would work on arsenic isotopes. Not only me, but a lot of isotopes. Work on the arsenic isotopes.
Okay, so thank you so much for the talks, to you, and thank you to Catherine also, and thank you to everybody who stayed until the end. And lots of people have been joining and listening, so thank you so much, all of you. And what I am going to ask Catherine, maybe if you can come into the screen, and maybe some of you who would want to come to the screen, I would like to take a little picture so that I can put it in our tweet. Maybe Nancy, if you don't mind showing up. Steve is there, Lex is there. Whoever is around and would like, the rest you are welcome to leave. Vesna, yeah, I think it would be nice to show faces, but I need, for the people who stay, need to show their face. Otherwise, you are welcome to leave, because I don't want to show just names. Or maybe it doesn't matter. I'll show. Oh, I don't even need the camera. I can just do it with the, sorry. Let me just do 4. Okay, I should be able to take the picture like this. Everybody smile. Thank you so much for joining. This was great. Very good. Not the same as doing it online. So hopefully we can do another one very soon. Thank you, everybody. Bye. Bye-bye.